everyone, welcome back to the third session of this workshop. This session is about talking about the Widefield microscope. So before talking that, let me talk you about the learning objective of this session. So we're gonna talk about Fourier Optics approach to talk about the propagation of the light. We're gonna show that lenses are able to perform Fourier transforms. So we don't use only lenses to make images. Lenses are able to do Fourier transform and switch between the space and Fourier domain. We're gonna talk about the relationship between the image and the spatial filtering. So how we can reduce the spectral bandwidth of an image using filters. And finally, all those concepts are going to get applied to a conventional light microscope. So let's talk about the first learning objective. So Fourier optics, the main idea is that optics can be thought about as a mathematical tool. So let's say that you have an image, right? So this is here the image of Fourier, and then we can assume that that image is a combination of different linear phase factors, like this kind of like plane wave. Obviously, the weighting of the plane wave is different, but the whole idea is that an object, a Fourier signal, so an image is composed with the Fourier spectrum with different wavelengths. Or backwards, the Fourier spectrum is composed by the signal in the space domain with different wavelengths. So that's how we're gonna talk always. So always we're gonna have this kind of dual pairs between the space domain and the Fourier domain. So super important, and when we are thinking about imaging systems, the system needs to be linear. So let's assume that we have an optical system, right? And we're gonna think about the optical system as a black box, and we're gonna have a particular operator that is gonna call S. So the operator is to move whatever signal you have in your input. It's gonna give you your output signal. So this is what we are saying here mathematically. Your input signal, so your operator of the system gets operated in your input signal to get the output plane. And the output signal, the input signal could be whatever you want. The operator, the system is gonna always have the same response. So what is gonna happen? So the system is gonna be linear if instead of having now one input signal, your input signal is a linear combination of two input signals. And we're gonna say that the system is linear if the same weighting is gonna happen to the output of the individual signals. So the alpha, because it's a constant, so alpha and beta, which are the weighting of the signal, the input signal, can move outside. So at the end, we're gonna have the same weight combination of your input is gonna get moved to the output signal. And why it's super important to have linear systems? Because then when the system is linear, when we can think about the output signal, we can think about as a convolution. So what we have here is the sum from minus infinity to plus infinity of your input signal, and then we have here h, where h is gonna be related with the response of your system, and this is the integral form of the convolution. So let me show you what is the convolution. So let's say that f is this kind of like blue signal right here, and the response of my system is the red rectangle. So let me show you again. So the red rectangle is the one that gets shifted. So you see like it's gonna keep moving, and every time for every x position, we're gonna have some overlay between the h and f, and that's how we're gonna get our black signal right there, which is the solution of the convolution. So the compact support of the convolution is gonna be always, so the G gonna have a compact support that is gonna be higher than the input signal. In fact, if F and H, both of them have a compact support function, so that means that they only have values within certain region, then the compact support of G is the sum of the individual compact supports. Alright, so as we were saying about Fourier domain, everything is about pairs, right? So wherever you have in your space, you're gonna have some frequency related. So so we have here G, right? And G, we know now it's gonna be the convolution between your input and then the response of the system H. So now if we're gonna know the spectrum of G, which the spectrum are gonna call with the capital letters. So the Fourier transform of G is gonna be the Fourier transform of a convolution, but due to the Fourier transform properties, the Fourier transform of a convolution becomes a product. So the spectrum of the output signal is gonna be equal to the product of the spectrum of F and H, where capital H, the spectrum, the Fourier domain of the input response, that's the system transfer function. And this system transfer function is telling us which frequencies are transferring from the input signal and in which weighting are they transferring. So I'm gonna skip a couple of math details. You have all the math details in this book, which is a really good book. But the whole idea at the end is like, if we are thinking about propagating light in Fourier space, so just like Fourier space, like nothing is within, the input response of the system, it's mostly a part of Boole's constant, where D are just the propagation and K is the Webb number. We're gonna have a quadratic phase factor, and this is true because we are in the paraxial approximation, right? So if we want to know now what is going to be the spectrum of a signal through free propagation, now the transfer function of the free propagation is still going to be a quadratic phase factor, because the Fourier transform of a quadratic phase factor is another quadratic phase factor. But if you're gonna see the distance d, that was the distance of the propagation, instead of being on the denominator, it's gonna be now in the numerator. But still, it's gonna be a quadratic phase factor. This is a super useful thing to remember always. Alright, so let's talk about what is the Fraunhofer approximation. So we already said what is free propagation, right? And we have the input response of a propagation as a quadratic phase factor. So let's put this convolution, write it down within the whole integral form. So they write the convolution in the integral form. So we're gonna have x squared plus y squared. It's gonna go outside of the integral, and then we're gonna have another quadratic phase factor going to x0 squared plus y0 squared, and now we have the multiplication within x and x0. So if we are in Fraunhofer approximation, in that region means that we are really far away. So the value of c is far away. So this integral is gonna go to 1, and when we remove that integral, what is gonna happen here, the expression that we have right here within the integral form is the Fourier transform of your input. So this is exactly a scale copy of the Fourier transform of your input signal F. So in the Fraunhofer regime, what we are saying is that the output signal that you are measuring at a distance c, it's proportional to a scale copy of the Fourier transform of your input signal. This proportionality depends on the wavelength and how far you are, but then you are multiplying with a quadratic phase factor. And this is true when the propagation distance is much larger than the size of your input and much larger than the size of your output. So you have two constraints, two conditions that you need to meet to be in the Fraunhofer regime. And at the end of the day, we're going to say that the diffraction patterns, which are the distribution of your output signal, are basically scale copies of the Fourier transform of your input. Alright, so let's talk about how lenses can perform Fourier transforms. So let's talk about 2F system, right? So you have here a thin lens, so a converging lens, and you have some thin transparency with a transmittance that is going to be F. And let's assume that we are illuminating with a monochromatic plane wave, right? So the light here, F, is going to go, it's going to free propagate at distance F until meet the lens. Then we're going to meet the lens, free propagate again to estimate what information we have at the image focal plane of the lens, which is also known as the back focal plane. Alright, so the first step is the free space propagation, right? So we have our input signal convolved with the input response of the free propagation, where now C is the focal length because the transparency is placed at the front focal plane of the lens. The next step, and this is going to call the output G, just in the plane just before the lens. So now we need to know what is the amplitude distribution just after the lens. So this is mostly what we have just before multiplied by the transmittance of the lens, which is a quadratic phase factor with a distance 2f. And now that is going to become our new input distribution. So that's going to become our new input distribution, and now we need to multiply with the input response just to go to the back focal plane, because that's the information that we want. That's the diffraction pattern that we want to know. Alright, so all those steps that you can solve it by solving the convolution integral, we can do it so much easily if you write this free propagation, the lens, and the free propagation using ABCD matrix. And the whole idea is that every step you put ABC matrix and kind of like the final system you're going to analyze. If you in your final matrix the b is equal to 0, that's the integral that you need to solve. And if b is equal to 0, then that's what you need to solve, right? So let me show you how that's going to work out in the real case. Alright, so we have this case, we don't have any aperture. So the first step is a free propagation. So this is the first matrix. This is the ABC matrix for the thin lens, and this is the matrix for the last free propagation. So you can multiply matrices, and that's our final matrix. In our final matrix, A and B are 0, and B are equal to F. So if we go back, then we're gonna know like the quadratic phase factor is gonna go out. So we're gonna write this output signal at the back focal plane of the thin lens. It can be written. We just need to solve this integral. The integral, which if you look the kernel of the integral, that's the kernel of the Fourier transform. So what we have at the back focal plane of a lens is just a scale copy of the Fourier transform of your input, where the scale factor depends on the wavelength and the focal length for your signal. So right now I'm just showing to you that at the back focal plane of a lens, where a transmittance, a transparency is placed at the front focal plane, we have the Fourier transform. Alright, so now that we have proved that the lenses can make Fourier transform, real Fourier transforms. So let's talk about the image formation and the spatial filtering. Alright, so in a microscope, at the end of the day, what we have are two lenses, right? So microscopes usually work in a 4F configuration. So what that means is what you have is the object placed at the front focal plane of the first lens. Then we know that at the back focal plane of the lens is going to be the Fourier transform. So that's going to become the input signal of the second lens. And then At the back focal plane of the second lens, what we're gonna have here is the image plane. And I'm gonna show you, so if you look the illustration, what you have here is that you have a F. So you are saying that your image, the output of the 4F imaging system, it's also the F, but it's inverted. So here, how we call 4F, so that means it's just summing the separation between the object and input plane, and because everything is placed at the focal length of the lenses and the lenses have the same focal length, that's how we have a 4F system. So we want to know what is the diffraction pattern and the image plane. How are we gonna get that one? So again, we're gonna do ABCD matrix. We don't have any aperture, so we can do all the process together. So the first one is it's a free propagation of a distance f from the input to the lens. Then we have the first lens. Then we have another free propagation from the first lens to its back focal plane, which this is going to be the Fourier plane. Now we have a free propagation of f from the Fourier plane to the second lens. We have here the second lens and then the final free propagation of distance f to arrive to the bifocal plane of the two lenses. So what I have done here is we already solved this in the previous case, so we're gonna have the same matrix exactly that they're gonna multiply, and we have here it's the identity matrix where we have minus. So b is equal to 0 in this case. So what we're gonna have here is that equation. So we're gonna have 1 over the value of a, L0, where L0 is the optical, is the geometrical distance within the input and the output plane. Then we have a quadratic phase factor that depends on the parameters C and A, and then the scale version of the input with A. So C is equal to 0 here, so these terms go away, and A, which is related with the lateral magnification, because the both lenses have the same focal length, we have minus 1. So at the end of the day, a part of this quadratic phase factor and the minus sign here, what we have is that the output of the Fourier system is just the inverted version of your input signal. That's why when you make images, the F is kind of inverted, goes back side down. Alright, so this is gonna happen when we have a Fourier system with no aperture. And at the end of the day, what you need to know is like, alright, so this is your input, here you have the Fourier transform of your input, and now in this Fourier plane usually is the plane where we put aperture, we put a pupil, so the pupil is gonna crop, it's gonna filter the spectrum of your signal, and now that's gonna become our next image. And then what we're gonna have at the end is the image of your clip, of your filter Fourier transform of your signal. Alright, so this is what we are saying. So now you have your Fourier transform before, but you are putting a mask, and the transmitter of your mask now is gonna be P. And we want to know what we have in the final image plane. So we're gonna repeat exactly the same stage, the same process, but now we're gonna go from the input signal to the Fourier plane. So this is what we're gonna have. So right, we know already that that's gonna be a scale version of the Fourier transform of your input, but now we have a mask, right? So whatever we have after that plane, the Fourier plane, is gonna be what we have just before the mask multiplied by the transmittance of the mask. So here, the transmittance of the mask multiplied by the scale version of the Fourier transform of your input signal. And this becomes now our new input plane. And we have again a lens placed in a focal configuration. So we have now F, the free propagation at distance F, the lens, and the other free propagation. So this is what we have now as the new input. So this is what is going to be here on the integral, and now we have here the kernel of the Fourier transform. So what we're going to have is the Fourier transform of your input with a scaling but the Fourier transform of a product becomes a convolution. So it's gonna be the scale version of the Fourier transform of the transmittance of your mask convolved with the inverted image. So this is what you're gonna have right now. So when we have a mask in the Fourier plane, a part of the quadratic phase factor, what you have is a convolution with the inverted input signal convolved with the scale version of the Fourier transform of the mask transmittance. And now, if we think about what we were talking about linear systems, we were saying that what we have here on the convolution side, that's gonna be object convolved with the response of your system. So this is the input response of a Fourier system. Okay, so the input response, the point spread function of a Fourier system is just a scale version of the Fourier transform of your mask. And that means that if you are assuming, so when we talk about the input response, it's like if you have an input point, so you have as the input signal, it's as delta function. That's where it's gonna be the output of your system. And the system is linear shift invariant because if you change the position of your input response, the response is going to be the same, it's just going to get shifted. So that's super important because that's why we can put everything as a convolution. Otherwise, different points placed in different places within the field of view is going to have different responses. So we cannot put the output as a convolution, we just need to solve the integral point by point. Alright, and if we know the input response of the system, we do the Fourier transform, so we know exactly how the frequencies are transformed. So that's the transfer function of our system. In this case, the Fourier transform of a Fourier transform is just your input signal, so that's going to be the transmittance of your mask. And now the scaling factor is going to go to the numerator, so it's going to be the wavelength and the focal length of your system. And here we have a minus signal because you are making the Fourier transform of a Fourier transform. So if you were doing the Fourier transform of an inverse Fourier transform, that minus is going to take away. But that's why it's the minus signal here. So let's talk about what is going to happen, right? So let's say that you have an object. So here, like, you have this kind of profile for a man. You have a mask in the Fourier domain, and you are using a Fourier Optics system, right? So what the mask is doing, it's cropping the frequency content of your object, right? And it's cropping the medium and high frequency. So you are creating a blur image. That's why the details, the high details, are getting lost. What is going to happen if your mask is different? So your mask, you cannot crop the low frequencies, but you allow the high frequencies to go out. So that in that particular case, the background of your image now is going to be black because that's the Parseval theorem, but the intensity of your image is going to the zero order frequency, which is placed at the center in the Fourier domain, right? So you are removing the zero order, so you are removing the intensity, so you become kind of like a black background, but you are allowing to have the high frequency. So what you are doing is you have an enhancement of the edges of your image. So that word is called kind of like dark field imaging, and that's to kind of like enhance the edges of your image and kind of allow you to have some kind of high contrast visualization. What is going to happen if now your object has two particular set of frequencies, right? So you have two grids, one vertical grid and one horizontal, and you are just allowing one of the frequencies to go out in and then blocking the other one. So in that way, what you are doing like selection of frequency. So you are selecting only, you are only allowing to pass the horizontal frequencies and blocking the vertical ones. Alright, so that's how you control. And you control optically, because that mask is something that you put in your optical system. You control what features you have in your microscope image, in your microscopic image. So let's talk about the last topic in this session of the workshop, right? So transmitted light microscope. A microscope is something that we have used a lot, and there are so many types of microscope. This is the first microscopes, and now those kind of complex commercial microscopes. But at the end of the day, a microscope is like a 4F imaging system, right? So let's remove all the lenses, all the relay system, but let's see the simple case. So you have an object that you place at the working distance of an objective lens. You have a mask, you have the aperture stop at the Fourier plane of the objective lens, and then that objective lens, they are working to send the image at infinity, so we don't have access to the infinity, so we need to use a tube lens to bring that image placed at infinity to a finite plane. So that's going to be the bifocal plane of the tube lens. So the objective lenses, they are formed with dozens of lenses inside to kind of correct aberrations, but we can assume that in theory that the lens does not have any aberrations, so the whole objective lens get replaced with a single lens. And as I was saying, this is a 4F system, right? So what we have is the object plane is placed at the front focal plane. The aperture stop with the mask is going to be at the bifocal plane of the objective lens. And then the aperture stop also is placed at the front focal plane of the tube lens. And my image plane is at the bifocal plane of the tube lens. So it's not anymore 4F system because the lenses, they have different focal length, but it's playing in a focal configuration, all right? So we can use the ABCD matrix. So we're gonna go from the object plane to the aperture stop, and then from the aperture stop to the image plane. So we're gonna do two. The whole system is gonna be divided into two ABCD matrices. And just to remember, that's what we're gonna say. Like, we're gonna characterize the ABCD matrix of every two steps, and we're gonna kind of figure it out where are the equations that we need to solve to kind of estimate the final distribution at the output plane. All right, so the first one is within the object and the pupil plane, and we have a propagation from the object to the objective lens, the lens, and then a free propagation from the objective lens to the pupil. And then the next step is gonna be from the pupil to the image plane. Again, we have a free propagation, the lens, and another free propagation. And if we do all of those together, what we're gonna have is that the amplitude distribution at the bifocal plane of the tube lens, which we're gonna call the image plane, that's gonna be the 2D convolution of the scale version of your object with a lateral magnification M, where M right now depends on the focal length of the tube lens and the objective lens. Remember that before the two focal lengths were the same, so that was 1. And now I'm taking the sign minus right there, so the object is still inverted, and it's gonna be convolved with the scale version of the Fourier transform of our mask, which we already know that. And if we want to do 3D imaging, so now what we want to know is like our object has a 3D extension. So actually we're going to have the 3D convolution of the 3D extension where the lateral magnification is different in X and Z. So in Z axis we have the M squared, and then the 3D response of a point source, which is going to be just the scale version of the Fourier transform of the pupil convolved with the free propagation input response of the system. So this is what we're going to call the 3D amplitude point spread function. What is going to happen a lot of time in microscopy is that our object is fluorescent, right? So the distribution of our object is incoherent. So what we need to do is convolve with the incoherent input response of your system, which is just the modulus square of the amplitude distribution. That's why we have here the modulus square. And this is what we're gonna call the 3D point spread function, which you're gonna find in the literature as the PSF. Alright, so we already have in the space domain. So in the space domain, what we have is the incoherent, the fluorescent distribution of your object, properly scaled in X and Z axis, 3D convolved with the input response of your system. And in the Fourier domain, we have a convolution, so that becomes a product. So the Fourier transform, the scale Fourier transform of your fluorophore distribution, multiplied by the optical transfer function of your system, where the optical transfer function is just the 3D Fourier transform of your PSF. So this is the PSF of a microscope. This is a iris disk, and then this is the distribution across the 3 axes. And then when we go to the Fourier domain, what we have is its compact support function. So that means it's outside in a certain regions. That here, for example, for the lateral dimensions, we have here the red circle, and then in the z-axis, what we have here is the bow tie, right? So what that means is the actual frequencies going to the center of the origin are not getting transferred, and I'm gonna talk to you what are the implications, and this is kind of the limit. So because the OTF is a compact support function, so the limits of the OTF are related with the frequency, right? And if we make the 3D distribution, it's like what we have here, that kind of donut shape, right? Where the actual frequencies in the middle are not getting transferred, are getting blocked. As I was saying, the compact support of the OTF gives us the resolution limit. So this is the lateral resolution and the axial resolution. It's isotropic for X and Y. So we have the same. This is the maximum frequency that is getting transferred to the system, and it depends on the numerical aperture and the wavelength of the system. And actually goes with is proportional to the square of the numerical aperture. Alright, so let's happen what it's gonna have. We don't have a 3D camera, right? So how are we gonna record a 3D object? So you place an object that they have different transverse sections, and you just focus one transverse section and make an image. Now you lateral displace the object, and you get another image, and you keep doing the whole process until you get a stack, a set of 2D images of the fluorophore distribution, and then you compose that numerically. What you're gonna see that it's gonna happen with a conventional Widefield microscope is that those are like areas that right now I'm kind of highlighting are part of the object that they are focused, right? But those objects, there are other areas that they are completely blurred. So they are blurred because they are transverse sections of different axial planes of the object, that they are somehow distorting the quality. So let me tell you in a different way. So in a different way, the technical way that we are talking a lot, it's about optical sectioning capability. So in other words, traditional, conventional Widefield microscopes, they don't have optical sectioning capability. So what that means is the in-focus information and the out-of-focus information, both of those information, they are present in each transverse section of the image, reducing the contrast and the visualization of your image, right? So this is because I'm pointing right here like the in-focus information that it's completely mixed with the out-of-focus information. So ideally, what we want to have is system with optical sectioning capability, right? And that's, for example, what is going to happen if we are imaging a 3D pollen, right? We have a pollen and we do the different transverse section of the pollen. Because the out-of-focus information, the contamination is so high, if we do the stuff, we don't want to see the details of the pollen grain. But if we were making the image using a microscope with optical sectioning capability, only the in-focus information is going to get imaged in every transverse section. So we're going to have a realistic idea of the 3D distribution and getting a real model or a better realistic model of the 3D structure of the pollen grain. So another way to know that the system does not have optical sectioning capability is with the integrated intensity. So the integrated intensity is just the sum of the PSF integrated along the x-axis. So this is the 3D PSF. This is the axial coordinate and this is the vertical. So what we're gonna do is for every z-axis we get the sum of all the points of the 3D PSF. And experimentally that is getting measured by if you have a fluorescent uniform object. Alright, so you're just getting, you scan it through the object volume, and the image that you are getting, you just get the mean value of the sum value of your intensity for every position of your layer, and that's how you you make the integrated intensity. And if you do that for the Widefield image, you're gonna have a flat response. So the integrated intensity is completely flat, meaning that there is no way to know exactly what is the actual position of the layer because the response of your system is exactly the same. So there is no discrimination of the actual position, and that is because the system does not have integrated intensity. So the integrated intensity is related with the axial distribution of your OTF, right? So in fact, if you have the integrated intensity, the Fourier transform of your integrated intensity along the z-axis is just if we make a profile of the OTF where the lateral frequencies U and V are equal to 0. So if you go here and you make a profile through the W axis, which is the axial frequency, you're just gonna have a single point, you have a delta. But the Fourier transform of a delta is 1. That's why here we have the flat top, right? So that's how, if we want to have optical sectioning capability, we want to discriminate the axial position of the fluorescent laminar shape, then what that means is we need to have some kind of narrower function of the integrated intensity, which that means we need the bandwidth, the axial bandwidth at the origin, at the lower frequencies of your OTF needs to be increased. So we need to put frequencies in the missing cone of the OTF. So those are two problems that conventional microscopes they have. The resolution is limited by diffraction because the OTF is a compact support with limited extension depending on the numerical aperture of the objective lens, and then there is a missing cone, meaning that every in-focus information in each transverse section of a 3D object is distorted with the blur information coming from the other plane, so we don't have any idea about what is the actual position of the plane. Well, I think this is the end of the third session of the workshop. We have revised how we're going to talk about propagation of the light using Fourier domain. We have proved that lenses can perform Fourier transforms. We have shown what is the relationship about image formation, what is the effect of an image depending on the mask that we place in the Fourier plane. And at the end, we have talked about the conventional Widefield microscope. We just need to thank again all the people, all the collaborators, and the funding to make possible this workshop. Thank you.